Hello, welcome back to another lecture of design of concrete structures, and this is going to be the fifth lecture on prestressed concrete. And so far we have seen different types of problems, and this is another variation of prestressed concrete, type 4 and 5. Uh, because previous problems we have seen the tendons only in the straight line tendons, actually either below the neutral axis or above the neutral axis, or there can be a chances of a bent up tendons like this. As you can see in the figure, this can be a chances of bent up tendons like this. Means a dip is more at the center, and when it comes towards the end, it can go through in coinciding with the neutral axis, or it is above or below the neutral axis also. So we will like this, it's in line with the neutral axis, or in other case it is above the neutral axis, or in other case it is below the neutral axis. So there are the three variations of this type of problem, actually. So let us take the first case, wherein the dip is more at the center, and there is no eccentricity. That is, when I say eccentricity, the eccentricity is actually a measure at the end, actually. If it is in line with the neutral axis, we should say that there is no eccentricity. Please don't consider this. Okay, eccentricity is at the point of application of the load, it is. So here it is in coincidence with the neutral axis. It is coinciding exactly with the neutral axis, so there is no eccentricity here. So let us see the case here. So let us think that there is a beam in which a central point load is applied, W is applied at the center, and the dip of the tendon is in a bent up tendon like this, and dip is more at the center, and as it comes to the end it is in close with the neutral axis. And let us say the theta is the angle with this tendon max with the horizontal. Okay, and the force P is applied here, actually. Okay, so as we can see here, this force P will have two components. One is vertical component, which is P sine theta for this side and this side. So what happens is, this load is applied downward, this W, the load is applied downward, whereas the P sine theta, the component, the vertical component of the pre-stressing force, will apply upward, actually. So what is happening is, as you can see in the second figure, there is a upward force which is because of the tendon pulling a 2p sine theta. It is acting upward. So your actual net load will be W minus 2p sine theta. The effective load will be W minus 2p sine theta. So this is an important point, actually. So the important of this value, the effective load, is this is the load we should use for finding out bending moment due to L, ML. ML is, here it is WL by 4. Don't take WL square by 8, because the load is a point load, vertical point load. So it is WL by 4. So for finding out a bending moment due to live load, we should use this W minus 2p sine theta. That is the inference of this here. So once the tendon is cut, so what happens is, there is a horizontal force P cos theta. You see here, vertical component is P sin theta, horizontal is P cos theta. It is compressing the section. Okay. So what is happening is, since the theta is very small, P cos theta can be taken as P by A, P itself. So the direct stress will be P cos theta, force which is P cos theta by area of the cross section, P by A. But since theta is very small, P cos theta can be taken as P, so direct stress is P by A, right? So in this case there will not be any moment. PE, that term will not come. PE by Z term, this term will not come. This term, this your PE by Z, PE by Z term will not come, because your tendon is passing exactly through this will not come, actually. The reason is, the tendon is passing exactly through the neutral axis. Okay, here at the neutral axis, this will not come. Yeah, this will be 0 because E is 0. So your upper fiber stress will be P by A because P cos theta by A, since cos theta is small, P by A. Then the load is the dead load will be acting down, right? Because always the dead load and live load will be acting downward only because it is a gravity load. So plus MD by Z. You know what? Why plus? Because it will bend down only. So top compression. So plus MD by Z plus ML by Z. Okay. So this term will not come. So this is what important. So let us do one problem. It will be more clear for you. A prestressed concrete beam 40 by 40 centimeter by 60 centimeter deep. This is 400 mm and 600 mm. The deep has a span of 6 meter. The span is 6 meter. The beam is prestressed with a tendon as shown below. It's a bent up tendon where center it is 160 from the bottom and top sides it is in line with the eccentricity. I mean in line with the neutral axis. So there is no eccentricity. External load on the load on the beam consists of a concentrated load of 180 kilonewton. So a concentrated load 180 kilonewton is acting at the center, which is a live load. Calculate the extreme stresses for the mid section. Effective prestressing force is 1200 kilonewton. So this P is given. Effective means when I say effective, it is final prestressing force is given to you. Okay, effective means after deducting all losses. So it is going to be the final P is equal to 1200 kilonewton. Yeah. So as a matter of fact, as we discussed below, so we need to find out the effective load actually, which is W minus 2P sin theta. Okay, same is the case here. So let us find out the sin theta first. Instead of that, let us find out tan theta. Then you can find out theta. Okay. So see, tan theta, this distance, tan theta is opposite. If you take this portion, this triangle like this, opposite side is this one divided by adjacent side is this one. Adjacent side is 3000 because total is 6000 the span. So from the center it is here 3000 and this height, the half is 300 because total height is 600, so half is 300. So 300 minus 160 is going to be 140. So tan theta you will get 140 by 3000, which is 0.046. Yeah. So since theta is very small, sin theta can be taken as tan theta. Okay, sin theta will be equal to tan theta. That is the point here. So your net load, because this is acting down, so and 2p sin theta, as we discussed before last okay, this 2p sin theta will be acting here opposite. Okay, so your net load will be 180 minus 2p sin theta. So 2 into p is 1200. Okay, and 0.046, which is tan theta. Since theta is small, sin theta is equal to tan theta. So you will get like this. So this value is it will come like 68 kilonewton. Okay, as you can see in the next figure, next page, net load will be 68 kilonewton. Now let us find out because our aim is to find out this one, sigma u is equal to P by A plus MD by Z plus ML by Z. Okay, so let us find out the bending moment due to live load. What is the live load here? Live load is 180 kilonewton minus 2p sin theta. So you got it 68 kilonewton. So 68 into WL by 4 because it's a concentrated load. So WL by 4, not WL square by 8. Yeah. So WL by 4 will give you 102 kilonewton meter. And bending moment due to dead load is going to be UD load. So WDL square by 8. So WD is nothing but the self weight. So 0.4 into 0.6 into 25 L square by 8. It will come around 27 kilonewton meter. So Z is BD square by 6, 400 and 6. So these are the values. So upper fiber stress is equal to P by A plus MD by Z plus ML by Z. Because P by A is a compression, MD by Z top compression, bottom tension, and sigma L is P by A minus MD by Z plus ML by Z. So this value, this will not come. PE by Z will not come because tension is passing through at the end it is passing through the neutral axis. So you will get upper fiber plus 10.3 and lower fiber it is minus 10.33 Newton per millimeter square. Okay, just square meter square. I think it is clear. So let us do another case wherein the tendon is having it's a bent up tendon only, having a dip at the center, and at the sides it is moving away from the neutral axis. So this is your eccentricity here. Okay, don't think this is your eccentricity. This is the eccentricity. Okay. So in this case also same situation will come. Will have your same case will come. So here also you will have your because of vertical component, this will be acting at upside, so 2p sin theta. So your effective load will be, net load is will be W minus 2p sin theta. Okay, then here the thing is that you will have your what do you call, you will have your PE term will come, because since this is of because once this is when the tendon is closed, you know, I mean the tendon is cut, so you will have your I mean what you say, your horizontal forces will come, horizontal component will come like this, P cos theta. I can write like this is a P cos theta, since theta is same, theta is very small, cos theta it can be taken as 1. So P cos theta, it can be written as P cos theta, it can be written as P itself, because the theta is very small. So I can write like this, P cos theta can be taken as P itself. Okay. So this term will come P by A, because this will create a compressive force, and this P and E will create a moment also. So P by A, because the only thing we should thing is this will bend because the eccentricity is the upside. So what will happen is this will bend like this, bend downward. So top will be compression, bottom will be tension. That is the reason PE by Z will come here, PE. So this is consider two cases. One is at end section, this section. So this section what happens is your bending moment due to WL square by 8 or WL square will be 0. So only end section you will have only these two things, P by A and PE by Z. Okay. Whereas at the mid section you will have this one, P by A plus PE by Z as usual, plus MD by Z and plus ML by Z, because this dead load will bend the section beam like this, level load also will bend the beam like this, top compression, bottom tension. So all this will be like this. So only thing is that when you calculate ML, bending moment due to level load, that is WL by 4, that W you should take this W minus 2p sin theta. Let us do the same problem which I have done before. Okay, same, all the data same, except tendon is just above the neutral axis. This is the situation. A prestressed beam 40 by 60 centimeter deep has a span of 6 meter. The beam is prestressed with a tendon as shown below, like this. Okay, the external load on the beam consists of a concentrated load of 180 kilonewton. Calculate the extreme stresses of the mid section. Effective prestressing force is 1200 kilonewton. Okay, same thing. So find out tan theta. Tan theta is this distance. Tan theta, when you find out tan theta, you should take this value, this distance from here to this, divided by this distance. So this distance you will get 190. Okay. And divided by 3000 you will get 0.063. So P is equal to 1200 kilonewton and E is your 50. So you should take E as 50. Okay. From the neutral axis it is 50. Tendon is 50 centimeter above, 60 mm above. So net load is W minus 2 sin theta. So you will get 28.8. W minus 2p sin theta, as you are discussed before. And that is 28.8 kilonewton. Then bending moment ML, it is WL by 4 because of the concentrated load. So 28.8 and 6 by 4 it will come 43.2 kilonewton meter. And bending moment due to dead load is WDL square by 8. You know it very well. It is the self weight of the beam, which is 0.4 into 0.6 into 25 into 6. That's the span. square by 8, so 27 kilonewton meter will come. So on Z is BD square by 6 you found out. So your upper fiber stress will be P by A plus PE by Z. The reason PE by Z is it will come plus. Why? Because your what I call your eccentricity is up above the neutral axis, so it will bend like this only because of this PE. So top compression, bottom tension. So plus PE by Z plus MD by Z plus ML by Z. Whereas lower fiber stress is P by A minus PE by Z minus MD by Z minus ML by Z. So I have calculated all the things here. P is this much, P by A is 5, PE by Z is 2.5, MD by Z is 1.125, ML by Z is 1.18. So you will get upper fiber stress as 10 and lower fiber stress as minus 0.425. Okay, so we will do another variation like this previous problem. It was above the neutral axis. Now the same case below the neutral axis, 50 mm below the neutral axis. So what difference does it make? Only difference is, since the neutral axis is the eccentricity is below the neutral axis, it will bend like this because of PE moment, P into E moment. Okay, so top will be negative, bottom will be positive. Remaining you can find out tan theta, right? So tan theta you should take this distance, the opposite side by adjacent side. So you 90 by 3000, it will come 0.03, and net load will be W minus 2P sin theta, which we have explained before. Then bending moment ML WL by 4 you will get. Bending moment due to dead load WL square by 8, Z is BD square by 6, and sigma U is equal to P by A minus PE by Z. The reason is this, it bend like this. Previous case it was plus PE by Z because your eccentricity was above the neutral axis. So because it will bend like this, bend down, which is bent up. Okay, similarly sigma L is P by A plus PE by Z minus MD by Z minus ML by Z. Since the eccentricity is below the neutral axis, the beam will bend up due to PE moment. So the top tension negative and bottom compression positive. That is the reason negative comes here. Okay, so the final value of stresses will be plus 3.75 at top and minus 3.75 at bottom. I think it's clear. So thank you very much.